In this video, I want to show you how it is possible to connect up to 8 7-segment displays, common cathode, to a Max7221 SPI chip. So what I want to do, let me go and let me show you first of all. Let me show you the hardware layout that I'm using here. So this is the chip, the Max7221 chip. In this specific example, I'm going to show you I'm just going to connect 3 7-segment displays here. And in this specific instance also, I'm connecting a 10K resistance. I will tell you later on. This is connected to iSet. Then also the SS, which is the chip enable of the slave, is connected to the chip select of the 7221. There's also a clock, where the clock is going to be connected to the slave. This is my Atmega 328P, of course. And there will also be where the data goes into this specific 7221 from the MOSI master out slave in pin. As you can see, this is not an intelligent device, this specific 7221. As it will not give any feedback to the master. It's only going to receive information, and then it will display that information. So what I want to show you also is, as you can see here, there's segments A, B, C, D, E, F, and G, and there's also a decimal point. And these pins are connected to the different segments. In other words, A is in parallel with this A, which is in parallel with that A. So they're actually connected in parallel. Whereas digit out 0, digit out 1, digit out 2, these will be the lines which is connected to the common cathode pin of the 7-segment display. So there's one here, and there's one here, and there's also another one sitting here. So what's going to happen is some data will be placed on the segments out here, and only one of these lines will be pulled low, which will basically activate that specific 7-segment display. So at one specific moment, you will see that only one definite 7-segment display will be showing something. But because of the speed that this switching will occur between the different 7-segment displays, the human eye cannot distinguish when this thing is switching off. So it will seem, if I can just get this to run in my program, I'm going to show you how we're going to display for U2. But as it seems, as you can see there, it looks as if everything is on at the same time. Whereas if I can just hold this, as I've said, only one of them will actually be active at one specific moment. And as you can see, the output in this specific digit 2 is a 0. This is why the common cathode is actually pulled 0, the common cathode pin. And this is why it will be displaying at that specific moment. So let me go over to the data sheet, first of all, of this specific device, which is this one here. And if I can just quickly go around the pins, this is my data in pin, this one sitting here. Of course, as I've said, this is going to go to digit 0, which in this specific implementation is this one sitting on the least significant bit position. Digit 4, for instance, will be, this is 0, 1, 2, 3, 4. So this will be that one sitting here. And so forth. The ground is ground, of course. This chip select or load, this is coming from the master microcontroller, the SS pin on the 328P. D out is actually can be connected to another 7221 device if you want to have more than 8 displays. And as you've seen, there are segments, segment A, B up to G, and also the the decimal point. So this is where these segment A and segment B and so forth, segment C, and then will be connected then. And of course, there will be the clock pulse, which is generated by the master unit. So what you see here is basically how it will be connected. As I've said already on my previous Proteus description, I said this is, if you place it between pin 18, and which is the I set pin, and plus 5 volt, something like I've done on my Proteus design, around about 10 kilo ohm. That is actually setting the brightness of your displays, of your segments. So the brightness is actually adjusted by that. You can either put in the resistance here, which I have done on my Proteus design, or you can also, in your program, you can actually go and make some changes in the settings and then change the brightness in that way. So there are two ways to do it. You'll see in my program, I've also programmed it to also set the brightness, because in Proteus it actually needs that command. Otherwise, all the segments will be switched off. But yeah, so in this specific case, I'm going to do both. But as you see now, if you only put the resistance in real life on hardware, that's all that you need. As I've said already, in my Proteus design, this is where this is going to digits 0 to 7, and this will be going to your segments. So we are now familiar with that. So let me go now to the data sheet, again to the data sheet. Let's look a little bit further in the data sheet, because I would like to start by explaining the format of the data going out of this specific device. Maybe before I go there, I can just show you here that, as you can see, when there's a clock pulse, which is the case here, there will be data. So on the leading edge, the data will be either sent or received. And if we go to this one here, if on your clock on the leading edge, which is this one here, and the data is actually read or sent or received in the middle here, that means that your clock polarity must be 0 and your phase should also be 0 in this specific control register, SPI control register. So CPOL and CPHA must both be 0. So when we do the program, you'll see I did not make it zeros, because if it starts up, it is going to be zeros in any case. So going back to the data sheet. What we will see here is that the serial data format is 16 bits. So this device actually wants to see 16 bits, but in normal, well, in any SPI communication, you can only send 8 bits at a specific time. So what will happen is 8 bits will be sent, and then the next 8 bits will be sent. But in total, this thing will receive your device, in this case the slave 7221, will receive 16 bits from D0 to D15. As you can see, D12 to 15 will be don't cares. So in my program, you'll see I've got a 0 there. There will be some sort of address, but from bit D0 up to D15, you can actually see that as a command, the command byte or the command address. And the data that will be sent can be found from D0 up to D7, but I'll explain it as I go along. Maybe the most important one to start with is the decode mode. In the decode mode, as you can see, it's also from D12 to D15, as it says there. It will be don't cares. So in that position, I'll place zeros. And then there's a 9. So I'm going to place hex 0 for those 4 bits there, and 9 in my command mode. But what does this decode mode mean? So if I can go maybe to my Proteus design again, let me just get this thing to run. As you can see in this example, I've got a normal value 4, which is between 0 and 9, or from 0 to 9, it's in that area. And here I've also got a 2, which is a straightforward decimal value. But here I've got a strange character. It's a not standard character, which I had to generate. So what we are going to do with that specific decode mode is we are going to do the following. I'm going to go to my program again that I've written here. So what I'll do first of all, if you want to look at this program, I will just go right to the top, and then I will scroll down, and if you want the program, you can retype it at some point then. Let me scroll down further, and there you go. So in this program, let's go to the program. What we've done here, what I've done here is basically to define that pin number MOSI is pin number 3, this one is pin number 5, and this one is pin number 2. So, and there's also what we've got here, there's a function that was generated which will receive a command byte, and it will also receive a data byte. That's the 16 bits I was talking about. So, but before I go to the execute and explain it, well, maybe I should, as you can see here, let me start with the main program. First of all, the MOSI, the clock, and the SS, they were created as outputs. Then what's also necessary is the SPI module unit must be enabled. The SPI unit is the master, the microcontroller is the master, and by making SPR0 a 1 here, we are actually, if I can go and just quickly show you here, we are actually making use of where SPR0 is a 1, and that's all I've mentioned. So this is a 0, SPR1 is a 0, and that is also a 0, making the speed, bitrate speed of this thing. In my case, I'm making use of a 16 megahertz crystal, so it's 16 megahertz divided by 16 gives you 1 megahertz, which is extremely fast. So that is just setting the bit rate. So we've got this execute function, which will thus give us the command, which is 9 in this specific case, and this is why I've started with this one. And then this value here, and as you can see, there's a 101 there. Now, what this means is, if I put 101, this one is related or referring to the digit 0 here. That, in other words, that's bit 0, so it refers to this one. If there is a 1 in here, like in this specific case, if there's a 1, it means that the data that you'll receive is going to be decoded. It will actually be decoded. So if I put in the data section a value of hex 02, it will display a 2. And this is why you will also see that bit number, this is 0, bit number 1 is a 0, and that means it is not normal decoding. So you will have to give the hex value to this function to tell it what character it must generate. So in this case, it's a non-standard character. So U is not normally a character for a 7-segment display, but you can display a U, and this is why you will have the data, this specific bit sitting here as a 0. So any strange character can actually be, if you want to strange character, place a 0 in there, and then it will basically look at the data and produce the correct display. So in this case, there's a U. I can have something like a capital letter F. I can have something like a capital letter E. I can have something like a lowercase d, or maybe an uppercase P, or a lowercase b, etc. So we can actually generate quite a lot of characters here by making use of the function, as I've said there, by making that specific bit a 0. Then you can create your own thing. If we look at, let's go and look at what does this execute 0A mean. So that is, as I've said, in hardware, because I've connected that specific resistance, the 10 kilo ohm resistance, because I've connected it, it should actually work perfectly in real life in hardware. But for Proteus, I have to set something, send something to this specific device. So let's have a look at 0A. So if I go to my data sheet again, you will see that the intensity can be changed by basically putting in A or 0A in the upper or the first byte, and those values, the data that can actually be sent to it, Let me show you. Sorry, it's on the same page. The data that can be sent to it is, it's going to be anything. If you send value of hex 01, that's your data. As you can see, this is between D0 and D7. If you put 01 in there, it is going to be 2 out of 16. That's the brightness. And if you actually go to 0F, the brightness is going to be 15 out of 16, which is almost totally, completely bright. What I'm going to do is I'm going to stop here, and I am then going to create another video number 2, which will follow directly after what I've done here. Otherwise, this video is going to become too long. So I'll be back and also add a video number 2. Thank you.